I'm going to be talking about Project Checmate and container networking. To start, the name Checmate is named after a hypervelocity railgun that was part of the Strategic Defense Initiative that was meant to stop bad things before it happened. So the drop K is intentional. But let's talk a little bit about who I am. I've been in the industry for about 10 years. And I started in operations, and I moved into networking and network engineering, and eventually into software engineering. And what I realized as I moved through the industry from the bottom of the stack up is that there's an incredibly large amount of inefficiencies because we've stratified these components of the organization. And I have a mission to try to make this better. And I think that containers are a technology that allows this to work together. And I've been using them since about 2011, before they were cool like they are today. And I think that they still have a ways to go until they can become ubiquitous in industry. But a little bit of an agenda. I want to talk about a brief history of how we got here, how we're trying to make it better, and how some of this might look in the future. But we need to start with a shared history of networking in the data center and why it works today. So I'm going to start about 10 years ago, 2007. 2007 was a radically different time. It was before the term DevOps was ever heard, and we had a clear differentiation of ownership in the organization. The data center was owned by a NOC. Systems were owned by sysadmins that were responsible for deploying software, and developers were responsible for features. And QA was a gate between all of this. And although this adversarial relationship between these organizations had benefits for stability, it made it so that software was incredibly slow to deploy to production. And it made it so that developers were typically oblivious to what was happening in production, making complex systems nearly impossible to run. Software was also very different back in 2007. Even though HPC had advanced in the SaaS industry and in enterprise, people were typically statically partitioning systems. And people were typically statically scheduling workloads on systems. And a given system would only do one thing and do that one thing very, very well. And this stratification of the organization led to everyone in the organization being responsible for one task and one task only. In that way, they didn't have a bigger picture of how the entire organization worked and how the entire stack worked, again, leading to inefficiencies. But applications were changing. And SaaS was growing at an incredible rate. And there became a race to ship faster. A year later, in 2008, the industry started to change. We began to see the idea of DevOps come about. And DevOps took off. Only a year later, in 2009, there was the first DevOps day. And suddenly that became the de facto job as opposed to a system administrator. We also saw this idea of the cloud become adopted. And it became sane to run your startup on the cloud. But enterprises realized that they needed to have the elasticity and the responsiveness and the agility that you could get from the cloud. And software in 2008 changed as well. We saw a popularization of open source tooling to be able to run systems at scale, to run data centers. We saw the likes of Jenkins and CI and CD tools to go ahead and remove that QA barrier and to automate that QA barrier. We saw the tools like Capistrano, so people could deploy systems to production without having to have intense knowledge of system administration tools. We saw tools like Puppet and Chef Takeoff, so system administrators could control underlying systems programmatically versus having to do everything by hand. But we also saw a popularization of stacks that had more complex operational requirements. The Hadoops of the world, the NoSQLs of the world, and these stacks could no longer be run by administrators that were application oblivious. And in 2011, we finally started to see the industry change. And that was due to some new enabling technologies. Although hardware-assisted virtualization had been there for a number of years, we were finally getting to the point where it was very, very low overhead. And there was an explosion in the number of applications, and hardware was growing faster than the rate of the applications were growing. And this meant that we had to partition systems in order to get better utilization of the data center. And we had to get faster time to deployment because we had greater applications. And that led to the rise of the private cloud inside of individuals' data centers. And the organizational stratification changed. We blended this idea of release engineering, operations, and QA into this DevOps thing. And we were able to gain efficiencies. But networking remained separate. And networking tried to have an answer to this. And that answer was software-defined networking. And the idea of software-defined networking was to introduce programmability to these proprietary segregated middle boxes. It was the idea that we would take these devices that were built by the likes of Cisco and Juniper that were using chipsets that were proprietary and software that was proprietary, and being able to have a common element or a common mechanism to program it. And it was the idea of endpoint oblivious networking. Networking never had access to what was actually going on in the box because these were VMs. This was software that was deployed by sysadmins that was independent from the folks that were actually running the underlying network. In the way that this actually was done was using a technology called OpenFlow. And it was a mechanism that came out of Stanford. And it was this idea, this programming language of kinds for SDN. And it was a mechanism to go ahead and control flows and control these intermediate elements that were doing forwarding. So if an originator had a connection that it wanted to make, it could go ahead and send that connection throughout the system. And if an intermediate device didn't know about that connection, it could ask an intelligent flow programmer element. And it could go ahead and give that route back to the intermediate device and take that and put it into its flow table and send this off. But unfortunately, OpenFlow was never successful. The vendors continued to keep their systems closed, and due to scale reasons, this idea didn't take off. Traffic matrices were exploding in the data center, and they were so unpredictable that we realized that this wasn't really going to work very well. And the idea of SDN never really took off. But then something happened, and that something was OpenStack. And OpenStack was this magic bullet to allow the consolidation of workloads via virtualization. And the belief was in many software-defined networking vendors decided to finally make offerings here. They took those existing boxes, those existing proprietary boxes, and finally opened them up to programmability because OpenStack had this idea that it was a bunch of building blocks and people could go ahead and swap in components as they required. But they still did the same thing. They replicated state, they replicated endpoint state, and they didn't take advantage of the fact that these endpoints were right next to these middle boxes. And after a couple years, we saw another change. We saw Docker come about. And Docker was what made containers popular, but generic containers existed before this. The idea of jails, the idea of software segregation. But what are containers actually all about? They're about user experience. They're about having the ability to deploy an application to a machine and having that entire system, or the idea of a system, dedicated to you and your application. And this comes through a set of abstractions. This comes through a set of abstractions like syscalls, mount namespaces, etc. And we get isolation. And isolation means that I can deploy a container onto a machine. I can deploy multiple containers onto a machine and not worry about them interfering with each other. And finally, it gives us system oblivious software. And this comes from the idea that I can build something on my laptop, take it to development, take it to staging, and deploy it to production without having to change that artifact. But what is a container? Where does the rubber meet the road? Well, there's two primary technologies that are predominant today. The first is namespaces. And they're what gives us these abstractions. These give us the ability to split up a system into multiple subsystems. And then we have C groups that do this resource isolation and that do this task marking. So we can go ahead and take a set of processes and say that they're in this hierarchy and isolate them as necessary. If we look at these namespaces, they tend to have a pattern. So the mount namespace was one of the earliest namespaces. And it had the idea that you could take a given file system and you could split that file system up. You could take given directories and remap them into containers or namespaces as you wanted. And from the container's perspective, it had the entire file system, or it controlled the mount table. PID namespaces acted in much the same way, where the host had one contiguous PID namespace, but given containers were able to control PID namespaces themselves, and they got their own PID1. There was a clear mapping and a clear level of delegation. And lastly, UTS namespaces, host name namespaces, work similarly, where everyone was acting on behalf of the host. Everything bubbled up to the host. But network namespaces were a little bit different. If we were to take the same idea from network namespaces and continue, we would say, well, if there's a device like ETH0 that's connected to the network, we would just mirror that into the container itself. But we didn't go with this method. We didn't go with the idea of mirroring. We didn't go with the idea of slicing up these devices. Instead, we decided to use this technology called virtual Ethernet pairs, VETs. and we relied on some magic to get traffic into the container. But this wasn't magic at all. This was just your standard net filter contract and routing subsystems that you get from the Linux kernel. But this was kind of odd because these subsystems were replicated inside of the container itself, because this veth abstraction only gave us a pseudo wire between the container and the host namespace. And we were, again, replicating all of the state. We were replicating the state that existed elsewhere in the kernel, and we were relying on heuristics to reassemble TCP connection tracking. We were relying on heuristics to reassemble all of the state. But why do we need this abstraction? Why do we need network namespaces at all? It seems like this shouldn't be important. Most software doesn't stress the network in any particular way. Well, let's talk about how applications are deployed. Typically, when you have a container, you have some set of base components. And these base components probably want to run on the same port. And in previous environments, the way that this was done is that we could give each one of these systems different IP addresses and give these base components the same port, and everything would be fine. But in the new world, instead, when we had a large number of applications or a large number of containers running on the same host, we had to dynamically choose these ports because we only had one IP address due to the limitation of these cloud environments, because of the inflexibility of the network. We need to let the scheduler choose the ports. If we peer inside one of these containers, it actually gets quite complicated. So first, we have to use that IP table's DNAT to get into the container. And then we have a bunch of services to assist in running these containers to make it so that we can be container oblivious in some ways. And one of the most common things here is this idea of a request proxy, where your client app that's making upstream requests is oblivious to the rest of the system. And it's the responsibility of this request proxy to talk to some sort of registry and undo that mapping. But is there an actual cost to this? And it turns out there's a massive performance cost. So IBM did a study a number of years ago where they took Redis in Redis's standard benchmarking tool and tested Docker's default networking versus KVM's networking. And they actually found that Docker networking was 10% slower in certain cases as compared to KVM networking. Percona earlier this year did a test where they measured transaction performance on containers versus non-containers, and in Docker's bridge mode, its default mode. And they found that there was a 20% decrease in transactional performance in these containerized modes. And this starts to make sense when you look at the networking solutions that are given in containers. It looks like we just took all of OpenStack, took all of the solutions that were designed for virtualization, and carried them over to containers. And somehow we brought the blight of virtualization with us. And this is what Checmate is here to solve. Checmate is meant to be a better abstraction. But stepping back, let's talk about use cases. Let's talk about where this actually is handy. Service discovery. How do we actually find the tasks that are in the system? How do we build one of the service proxies? Well, we need some kind of directory. In that slide earlier, I had the registry. And one of those implementations of the registry, one of the implementations that we have in our system is called Mesos DNS. And the purpose of Mesos DNS is to take state from the Mesos master, the system that knows everything, and take its HTTP API and serve it over DNS. And it uses a standard mechanism called DNS SRV records. And these SRV records have all the metadata you'd want. You have port information, priority information, weights, et cetera. And what I thought was, well, everyone has DNS, right? And even glibc has a bug open for it. If glibc supports it, everyone has to support it, right? But this bug was opened in 2005. And it looked like the authors of glibc had no intention of supporting this. And we saw this throughout the industry. We saw this throughout the industry where no one wanted to change how DNS worked because it was such a complex system that people were afraid of changing it and modifying it. And what people really wanted was this abstraction of a load balancer, a single point that abstracted all of their services, a single IP address and port or a single host name and port that was all of their services. And they didn't want to worry about how this all worked. Tyler gave a really good talk yesterday about load balancing, and load balancing isn't really about how to distribute load. It's people want simplicity. And our first try of this was why don't we use LD preload? And for this, we have to step back. We have to talk about how these socket calls work. And if any of you have written socket code before, you know the connect sys call is one of the first calls that you have to make in order to wire up your TCP connection. And when your task makes this call, it doesn't typically make it directly to the kernel. It goes ahead and uses a libc that converts this down into a kernel syscall. And that libc knows these syscall numbers, and it passes down the data structures transparently. But if we introduce LD preload, we're able to then introduce a shim, and instead of people having to connect to specific IP addresses and ports of these services, they can pass a canonical name like Redis port 8080. And we can have a shim that can consult an external service like Mesos DNS, a directory, and rewrite that address when it gets passed down to glibc, and then gets passed down to the kernel. In what we want is this. What we want is the ability to lie to the container and connect to a given IP address and forget pure name to work. We want to be able to have a preservation of the standard APIs that we know how to use for socket programming. But it turns out this doesn't work. And because of Go and in other languages, there's been this resurgence in static linking. And static linking is basically taking that conversion component and putting it into the actual binary itself, so we can no longer insert that shim. And it also opens us up to time of check, time of use issues. So if we go ahead and look at this, for a given buffer in memory, it could get passed down to the shim, and the shim could go ahead and rewrite it to a good value, to a safe value. But that process is still running in the background. It could have another thread running in the background. And when that buffer gets passed down to glibc, the program could rewrite it to some nonsensical value or to some evil value if we're trying to do something like security. And although there exist mechanisms like C-group freezers and SIGSTOP to prevent this, they have incredibly high performance costs, and they're incredibly complex. So we thought, well, what else is there? What exists below that syscall layer? Well, there's the TCP stack. And is there anywhere in the middle that we can easily hook in? And it turns out there is. There's these Linux security modules that already exist. And there's a number of them that you might have heard of already. AppArmor, SE Linux, SMAC. But these are all programmed using restrictive DSLs, restrictive policy languages that typically lack extensibility. And they were created in a time before containers. For example, SE Linux descends from the early 2000s, where the NSA was trying to build a hardened Linux project. SMAC came from similar origins. In this idea of continuing to introduce new policy abstractions makes these DSLs unwieldy. So we thought, well, what if we change the way that this is done? What if instead of having these policies be in DSLs, we introduce the ability to run programs within the kernel itself? What if we can run these BPF programs inside of kernel space safely, and intercept that syscall and manipulate it? And what if we're able to take these filters, what if we're able to take these BPF filters and use the classification that we got from C groups in order to only affect certain processes? But I mentioned this idea of BPF, these in-kernel programs. What is BPF? Many of you have probably heard of BPF, the BSD packet filter or Berkeley packet filter. And it's a technology that's over 20 years old. It's a tried and true proven technology. And it's basically just an in-kernel virtual machine. And most of you have probably used it in the likes of TCP dump or Wireshark. And this was classical BPF. Classical BPF was a very, very limited virtual machine where we had 2 registers, a very tiny stack, only access to integer arithmetic. But we saw a massive number of use cases come about. Initially, it was only designed to do socket filtering, but we saw it become popular in other networking subsystems. It turns out that the PPP subsystem inside of Linux is largely implemented in BPF, even though it's actually in kernel C code. And one of the biggest turning points was in 2012, Google, in their Chrome project, announced this idea of seccomp sandboxing, where they were using this BPF filters to classify syscalls and prevent people from making malicious calls into the system. And there became an obvious need to extend this. And that's what led to this idea of eBPF. And eBPF is a massively more capable virtual machine. We have 10 64-bit registers, a much larger stack. But that's not the interesting part of it. The interesting part of it is the performance gains that we're able to achieve. And that's because it's jittered to x86 64 code. It's also jittered to ARM64 and S390, and then a few other architectures. And this is done because it's a restrictive VM that has type safety, and it has runtime safety. And this is done because we are able to prove that there's no unsafe accesses. And this is because that we're able to attribute types to pointers since we know how the programs work, and since we know the data structures that are being passed around. And we're able to ensure termination because we prevent people from jumping backwards. So we don't need to worry about programs that run forever. And the way that this actually works is that you have a user space controller. And this user space controller assembles some high-level code. This high-level code compiles down via LLVM into BPF bytecode. And that BPF bytecode gets passed into the kernel through the verifier. And the verifier goes ahead and jits that and turns that into x86-64 executable code. So we're not constantly having to take this BPF code and interpret it. The user space controller is able to influence the actions of this BPF program by using these BPF maps, which are basically just shared data structures between the kernel and user space. There's several BPF maps that already exist, like arrays, hash maps, and ring buffers. And we're now able to take this policy and implement it in C, or implement it in any programming language that we want. So this, for example, says that we don't want people to bind to a specific range of ports outside of 31,200 to 31,300. And it gives the user an immediate piece of feedback that these ports are not allowed to be binded to. But what are the actual benefits of this? This is a lot of complexity, and this is a lot of work to say that you can't bind to a given port. Well, the first thing is that it's impossible to avoid. Being in kernel prevents this time of check, time of use problem. And all of those data structures are already copied into the kernel before we check them, and before we verify them to be safe, and before we verify that they're accessing valid values. If we rewrite them, again, it's in kernel memory, so there's no way that a user can maliciously change them. And it brings back that standard BSD API that I was talking about earlier. It allows things like get peer name to work, and it allows things like receive from and send to actually tell you who you're communicating with. And this finally makes it so that we can use smart clients with container networking without having to worry about application layer gateways that are able to go ahead and understand how these protocols work and use heuristics to rewrite the traffic so it actually is able to connect to the given hosts. And we're able to introduce new syscall extensions. We're able to add new calls that you might want for container-specific use cases. So what are some advanced use cases for this? The port problem that I talked about earlier, it's possible to do using traditional IP tables. Let's talk about one of these use cases, which is an isolation use case. How do I prevent my container from exhausting my ephemeral ports? This is impossible to do with the likes of IP tables because they don't have this idea of group by. They don't have this idea of classification by container. And it turns out we can express this in a C program. We can express this in a C program, and the code doesn't actually matter, but it's succinct enough where someone can wrap their head around it. And it only compiles down into several hundred instructions. So it's not taking a given hit every time there's a packet. It's only taking a given hit every time that there's a syscall. And we can ensure things like we capture every free call and undo the work that that initial program did. Another use case is load balancing. So this given program here is able to go ahead and take the sock adders that are passed into the kernel, do a BPF map lookup, and rewrite those socket buffers so we connect to a new host. And these Linux security module hooks are pervasive throughout the kernel. They're everywhere. They exist in auditing. They exist in the file system. They exist in quotas. But what about performance? Does this actually have much of a benefit? And what is that benefit? Well, it turns out that we ran a similar test to the IBM test, where we ran the Redis benchmark tool against Docker bridge networking versus Checmate. And we found that we were able to get 3 times the number of operations per second when we were creating a new connection per request, and the requests were very, very tiny. And we found that in many environments, this is actually a typical pattern where their applications aren't keeping these request pools open because they don't want to preserve state across requests since there's an inherent cost to it. And we found that latency was 1/3 using Checmate as compared to the IP tables technique. And some of this makes sense. Some of this makes sense because we're able to do this once per syscall as opposed to having to do it on every packet. And these data structures are persistent. But you might ask, well, what about debugging? How do I tell what my programs are actually doing? If this is all happening in the kernel, I can't use my tools like tshrk. I can't use my tools like TCP dump. Well, we have a way to exfiltrate data from the kernel. And that's those ring buffers that I was talking about. So these BPF programs can go ahead and write to these shared ring buffers, and the user space controller can fetch these and expose these to the user. And what about a control plane? That's the most interesting part of this. We already have one that we're using inside of DCOS, our commercial product. It's called Navstar. Navstar is a control plane that goes ahead and talks to all of the Mesos agents and builds global state, and then is able to push this data into the kernel. And it's able to store this in a backing CRDT key value store that's replicated to all the agents. But how long until this ends up in your data center? How long until you can use this? Well, kernel patches are still in development. But the big thing that's preventing us right now is we're interested in building a higher level language. And we're looking at many tools from functional programming to do this. So that really complicated C program that I showed you earlier to go ahead and count ephemeral ports, rewritten to Erlang, is an incredibly succinct program. And this functional programming is a lot more natural, because we already have the idea of types in these languages. And the type systems are quite healthy in these languages. We already have the idea that we're not supposed to jump backwards because we don't use loops. We can leverage the in-kernel tail call instruction to go ahead and build these programs up. And the way that we can take an Erlang program and compile it into this is that we can take every sub-stanza of that Erlang program and turn it into an individual C function, transpile it to C, and then rely on the Clang auto inliner to determine which components have to be inlined and which components can be tail called, and then put those into the kernel as different programs and tail call between them. But here's a challenge that we don't yet know how to solve. How do we continue to cater to the stratification? How do we continue to cater to the fact that networking and network engineering and systems in some environments is still a separate organization and still a separate set of concerns? And how do we push people to upgrade the kernel? It turns out this is one of the funniest things that we found is that people are more than happy to run 5-year-old kernels, yet they want to be able to run things like containers. They want to run the newest technologies alongside their existing containers and existing kernels. So what did we learn when we were doing all of this? The first thing that we learned is that we're probably doing it wrong today. We're probably doing containers wrong, and the abstractions that exist today may be at the wrong level. In programmability is probably the only way to fix this. The other thing is that we realized that if we want performance, endpoint integration is key. Without having control over the entire stack, there's no way to squeeze out every bit of performance from the system that we can. But fortunately, the future looks bright, and there are primitives that are coming to make this easier. Ask the question, with programmable filtering, what would you do? Thanks.
Do we have questions? Nobody?
Kind of an aside there, Erlang. What was the CRDT key value store you were using?
So that's something I built. It's called lashup.
Okay.
It's an open source project.
Okay. What did you say it was called?
Lashup.
Lashup.
Yeah.
Okay.
We're looking for contributors.
Okay.
Oh.
Hi.
Hey.
So we've done various things at Fastly using IP tables and then ended up converting them into kernel modules later in order to avoid IP tables for exactly the reasons that you mentioned. So you talked about this primarily from a container networking point of view, right? But what else can you see that this could be useful for? So
it turns out that the actual use cases for this aren't primarily for containers. They're primarily for people who want to run secure systems. Any time that you can manipulate those syscalls and do things like change the interface that a given socket is bound to, it's beneficial. But it turns out that there's not very much funding in high security systems, but there's lots of money in containers. So yeah, that's why the talk is about containers. As far as the in-kernel thing goes, kernel modules are really hard to develop. People are really afraid of the kernel. It's friendly, it's nice, it's C code, it's great. But for some reason, as soon as you say the word, you have half the programmers in the room leave. So BPF and being able to compile Erlang and run it inside of the kernel is meant to make this somewhat easier and more approachable. So the cost of a kernel developer isn't hundreds of thousands of dollars, and they aren't super rare.
So I have another question. Would this be relevant for using raw sockets from within Erlang?
In what sense?
Well, it's not possible to directly use raw sockets from within Erlang, but I believe there are libraries which use, in order to use it on non-Linux systems, to use Berkeley packet filters in order to access raw sockets. Just wondering if this could be a kind of a cross-platform solution for that using Erlang.
So the Erlang here isn't actually Erlang at all. It's not running in Beam. It's compiling into BPF and then running inside of the kernel. So it uses a restrictive version of Erlang. So we have the ability to do things like lightweight processes in the kernel using BPF, but we don't have all of the typical facilities like hot code reloading and OTP available to us. But if you want to run a web server or write a web server in the kernel, you totally can using eBPF in Erlang. You just don't have OTP or Beam.
Right. Anybody else? Okay, let's thank our speaker.